Okay, welcome to the helper video for the zombie apocalypse. So hopefully you can read the first two slides by yourself. Let's go to slide 3. So on slide 3, explain each of the variables. What do they represent and where the parameters come from? Okay, so the variables are h sub t minus 1, z sub t minus 1, h sub t, and z sub t. And then the parameters are the 0.8, 0.1, 0.2, 0.9. So basically relate these two equations back to the information on slide 2. Okay, so after you've explained it, then I want you to write it as a matrix equation. So when you write it as a matrix equation, you're going to take the parameters out of this system of equations, and they are going to become their own matrix. And we're going to use that matrix for the next step on slide 5, which is question 3. And we're going to use this equation. This is the characteristic equation is the name for this equation. It is asking you to find the determinant of this matrix, which you are just putting in a minus lambda to the A and the D from the matrix that you made on this problem here on slide 4, question 2. So then when you find the determinant, you want the determinant to be equal to 0, and then you're going to be able to solve it. So I'm going to help you with that first. So let's see if I can click over to Zoom and share my camera. So this is going to be interesting to see how my technology works out here. So I'm going to share my camera, which is out of focus. That's good. Let's focus it. Here it comes. All right, so here's my matrix. Now, in order to do the characteristic equation, I'm going to be taking the determinant. We use the little absolute value bars to represent determinant. 0.8 minus lambda, 0.1, 0.2, and 0.9 minus lambda. And I want to set it equal to 0. So to get the determinant, and this is in your formula packet, how to find the determinant, you multiply the A times the D, so 0.8 minus lambda, times 0.9 minus lambda, and subtract the B times the C. So 0.1 times 0.2, and set that equal to 0. So when you multiply this out, you're going to get a quadratic, and you could try factoring it and solving for lambda that way, or better yet, use your handy dandy graphing calculator, type it in, and get your X-Intercepts. In fact, you could actually type it in right now. Now that I think about it, you don't even have to simplify it. So let's go ahead and do that. So if I put this in, I have parentheses, 0.8 minus x. I'm going to use x, of course, for lambda because I don't have a lambda on my buttons here, times 0.9 minus x minus 0.1 times 0.2. Now, if I graph that, it should give me a parabola. There it is. And I need to find my x-intercepts. I'm going to find my x-intercepts. So I'm going to do second calc, find my zeros, get my x-intercepts, left bound, right bound, guess. And it says x equals 0.7. So that's lambda equals 0.7. And then for the other one, left bound, right bound, yes, and 1. So lambda equals 0.7 and lambda equals 1. Okay, so I didn't even have to do very much hard work. I just had to enter that into my calculator. If you were doing this on a test, you should probably make a little sketch showing that you graph this and say, GDC, graph and display calculator. And this was a horrible sketch, sorry. Make your sketch better than mine. All right, to show how you got your lambdas. Okay, so there are my eigenvalues. So then to get my eigenvectors, what I need to do is I need to put these, I'm going to put them back in one at a time into my, my matrix here. So I'm going to have 0.8 minus, let's go ahead and use this one first, 0.7. And then I got my 0.1, my 0.2, and 0.9 minus 0.7. And then if I multiply that by I'm just going to go ahead and just use X and Y for right now. I mean, I could have used my H and Z, but just for simplicity's sake, I'm just going to do X and Y because now I'm trying to find my eigenvectors. So my eigenvectors are when I have this matrix times XY, I should end up with 0, 0. So if I simplify this, I get 0.1, I have 0.1, 0.2, and this one also would be 0.2. 0.9 minus 0.7 is 0.2. And then I have my X, my Y equals 0, 0. So now if I multiply these two together, I'm going to write a system of equations. I get 0.1x plus 0.1y equals 0. And then the other one, 0.2x plus 0.2y equals 0. And now if I solve this for y, I'll move my x to the other side. I get 0.1y equals negative 0.1x. Divide both sides by 0.1, I get negative y equals negative x. Okay, so this is a problem with my zombies. If I were to graph this line, I would have a line like this, and my zombies and my humans are only going to exist in the first quadrant. I can only have positive humans and zombies. So this eigenvector is useless to me. The eigenvector here would be, it's just the slope, right? If I take this and I change it to a vector, I just want the slope. How far over and how far down am I going? So I'm going over 1, down 1. So if I make this into a eigenvector, it's over 1, down 1. There's my eigenvector. And this eigenvector is useless to me. All right, hopefully this one's going to be better. So if I do lambda as 1, I'm going to run through the same process again. So I'm going to have 0.8 minus 1, 0.1, 0.2, 0.9 minus 0.1 times xy is equal to 0. And so now I'm going to have, this is going to be negative 0.2, 0.1, 0.2, and this is going to be, oh, what am I doing? Why did I write 0.1? Sorry, minus 1. That's going to be negative 0.1 times that by my xy equal to 0, 0. And I'm going to get negative 0.2x plus 0.1y is equal to 0. And notice I'm going to get the exact same thing for this one. 0.2x plus, sorry, it's going to be the exact opposite. Never mind, let me write it down. So 0.2x plus negative 0.1y equals 0. But if we simplify these, okay, if I move my x over to the other side and then divide by 0.1, so let's go ahead and simplify this. So I'm going to get 0.1y is equal to 0.2x because I'm adding it to both sides. Divide by 0.1, I'm going to get y is equal to 2x. And if you simplify this one, you will get the exact same thing. Okay, so if I graph this line, y equals 2x, well, that would be like this. And this one is in the first quadrant. It does have to do with my humans and zombies because I can have positive numbers for both humans and zombies. And my slope is over 1 up 2, over 1 up 2. So my vector, my corresponding eigenvector here would be 1, 2. There's my eigenvector. All right, so this eigenvector makes sense. This is basically saying that the equilibrium of my zombie human function is going to be 1 human for every 2 zombies. This was my H value, was my humans, and my Y value was my zombies. Okay, so I found my eigenvalues and I found my eigenvectors. So now I'm going to go back to the slide deck and see, does any of this make sense? So here is my question. Find the eigenvalues and eigenvectors. So I did that. And then for the next question, oh, look, you should have gotten 1 and 0.7. Oh, I gave you the answers. Now add the A and D values from your original matrix and compare it to the sum of your eigenvalues. I'll let you do that. I don't think you need my help with that. Okay, now here's where my questions got really sloppy. Okay, it says use your eigenvalues to find your eigenvectors. Oh, we already did that. I asked this question twice. Sorry, that was really silly. I shouldn't have asked this question question twice because I accidentally asked it over here on question 3. I should have just said to find the eigenvalues on question 3, but I didn't. I accidentally asked for both the values and the vectors. So on here, it's just asking you for those eigenvectors. And then it says, notice that one of these eigenvectors has a negative value, which doesn't make sense in the context of the problem. So you can throw that one out. All right, so sorry about that. We already answered this question back on slide 5. Okay, you don't have to actually do it again. All right, so what does this mean? The eigenvectors tell us where the system will end up if the process is allowed to repeat itself over and over again. So what is the equilibrium number of humans and zombies? Well, we know that our total number has to equal 300 because humans are becoming zombies, zombies are becoming humans, but nobody's actually leaving the system. Nobody's dying, nobody's coming, nobody's going. They're all quarantined inside of Cappuccino High School, if you remember the original storyline. So my number of humans and my number of zombies has to add up to 300. And I know I have to have twice as many zombies as I have humans. So I can actually write a system of equations for this. So let's go back to my camera. Okay, so I know that my number of humans plus my number of zombies has to equal 300. And I know that I have to have twice as many zombies as I have humans. So the number of zombies is going to be 2 times the number of humans. My z here has to be 2 times the number of humans. So I can replace my z with 2h. So I can write h plus 2h is equal to 300. So 3h is equal to 300. So h is equal to 100. So there would be 100 humans and 200 zombies is what my equilibrium population would be. Okay, so let's go back to the slideshow. So now the next thing is we can take this a little bit further, and it's asking you to learn about something called diagonalization. And I had to watch a whole bunch of videos to figure out what they were talking about. And what is going on here, let's see. What is going on here is if you have a matrix A, so our matrix was our starting matrix, that 0.8, 0.2, 0.1, 0.9, that matrix, it is diagonizable if you can write it in the form of P, matrix P times D times the inverse of P, where P is made up of the eigenvectors of your matrix A, and matrix D is made up of the eigenvalues. And notice the order is really important here. See how it says eigenvector 1, x sub 1, and x sub 2? X sub 1 is the first eigenvector. So my first eigenvector I found was 1, negative 1. And the second eigenvector I found was 1, 2. And then when you write the corresponding D, which it stands for diagonal matrix, you have to make sure that you put the lambda for the first eigenvector, put that where lambda sub 1 is. And then lambda sub 2 has to be the eigenvalue for the second eigenvector. So the order, like a lot of problems with matrices, the order is important. Don't mix them up. Okay, so then we have a further little information here. It says if you can write this matrix A in this form, P, D, inverse P, then there's a shortcut for taking a matrix to an exponent. A to the n is equal to P, D to the n times the inverse of P. So why do we care? Well, the reason why we care is because if we wanted to run our zombie human experiment many, 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 many times and see how many humans and zombies there ends up, there's actually kind of several ways we can do it. First of all, we can find the eigenvectors and eigenvalues, but there's actually kind of a shortcut. What you can do is you can just take the original matrix, and let me get another piece of scratch paper, and I'll show you what's going on here. So let me switch back over to my camera. Okay, Okay, so if I take that original matrix, 0.8, 0.1, 0.2, and 0.9, and let's say I want to transform my original population 48 times, right? Because we said we're going to do it for 48 hours. And see what happens to the population. I can do that by just taking the transformation matrix and raise it to a power. Say I want to do it for 48 hours. I can raise it to 48 hours, to the power of 48, sorry, and then times it by my original population. So let's say, I think I said, let's go with 150 of each, okay? And then what I can do on my calculator is I can put this in, and you're going to see that if I put this into my calculator, we're going to get really close to 100 and 200. So check it out. So I'm going to put in my original matrix. So I've got 0.8, 0.1, 0.2, and 0.9. Okay, and now I'm going to raise it to 48th power. Now I'm going to multiply it by my original population. So let's say it was 150 and 150. And if I hit enter, look at that, 100.000018 and 199. I really get close to the exact value that I got with my eigenvectors. So I can raise my transformation matrix to an exponent and multiply it by the original population, and I will get approximately the same answer as I did when I used the eigenvectors. Notice I didn't get an exact answer. I got an exact answer when I did it with the eigenvectors, but you can do this method here and get an approximation. So you can take your transformation matrix, raise it to however long, however many times you want to repeat the transformation, and multiply it by your original population, and you will get an estimate, in this case, a really good estimate, of the equilibrium population. Now, here's the problem though. What if I wanted to find out what happened after 200 days? Let's say I wanted to do 200 days. Well, I'm going to go back up here. I'm going to copy that equation. And first of all, actually, before I do that, something cool. You can see, doesn't matter what population I start with. I'm going to start with 0 humans, and I'm going to have 300 zombies. So check this out. If I start with no humans and I have 300 populations and I let this go for 48 hours, look what happens. I still get 100 humans and 200 zombies. So the starting number actually doesn't matter. Oh my gosh, I didn't realize that until I started messing around with this on my calculator. The starting number didn't matter. And I tried it again. I did, what if I start with 300 humans and no zombies? Exact same thing happened. I still ended up with the same equilibrium situation where I end up with 100 humans and 200 zombies. It was absolutely amazing. Okay, so now back to what I was saying. If I want to try this and I want to let the experiment run for more than 48 hours, say I want it to go for a long time, I can go ahead and change my exponent. So let's say instead of 48 hours, how about I want 480 hours, 480 hours. We're going to go a really long time, okay? And then I hit enter. Let's see what happens. I get an error. So at this point, my calculator won't do it. My calculator is like, I can't handle it. The value entered is not allowed in the function or command because it's trying to take this matrix and multiply it by itself 480 times, and it's just can't do it. So this is why we have the next thing in the problem. This is why we have the diagonalization issue. Okay, what am I doing? I need to minimize this. Here we go. So if I go back to this diagonalization of a matrix allows you to take the matrix, say A, to a really high exponent. If you can rewrite your matrix A, in my case, my matrix A was 0.8, 0.2, 0.1, 0.9. If you can rewrite that in the form PD, p to the negative 1, then you can take that diagonal matrix and raise it to an exponent really easily, okay? Because when you have a diagonal matrix, so the diagonal matrix is just going to be our eigenvalues, right? And what were our eigenvalues? They were 1 and 0.7, or 0.7 was the first one and 1 was the second one. You can take that to the power of 480, no problem. My calculator will do that. But my calculator will not take the matrix up to a power of 480. So this little formula here is if you want to do a matrix and raise it to a high exponent, this allows you to do it without straining your technology. Okay, there gets to be a point where even computers are just like, I give up, or it's going to take it too long to do it. In this case, I found out that 480 was over the top that my calculator could handle. Okay, so this diagonalization is done basically as a way to help the technology get do these matrix raised to a power. So now, if we move on to the next question, where is it here? Blah, 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 blah. Nope, that's not it. Where is it? Where's the question I want? Here it is. On slide 10, question 7, find the diagonalization of A. That all you have to do is take your eigenvalues and your eigenvectors, and you're just going to write down what is the matrix P, what is the matrix D, and what is the inverse of P. You're just going to write those down. Okay, that's what you're doing on 7. And then on 8, you're going to go ahead and multiply them out and show that it's the same as A up here. A is 0.8, 0.1, 0.2, 0.9. Okay, so for question 7, you're just writing out this equation, A equals PD and inverse P, and you're substituting in the P matrix, which is the matrix of the eigenvectors, the D matrix, which is the diagonal matrix of the eigenvalues, and then the inverse of the eigenvector matrix. Okay, so number 7, you're just substituting in the matrices into the equation. And then on question 8, you're actually multiplying it out to show that the two sides of the equation do equal each other. And then you're going to use, you're going to just raise it to the power of 4 because your calculator can handle that. It can take A to the power of 4. And you're going to show that those two, you're going to verify that this equation also works, okay, on question 9. And then you're going to do it again like I just showed you. You're going to see how you can get an estimate for the number of humans and the number of zombies by just using an exponent on the transformation matrix. But notice you don't get the exact value. By doing it the long way and doing it with the eigenvectors, you get an absolute exact answer. Here, we're just getting an estimate. All right, then when it's your turn, I was asked the question, hey, if we get a pretty decent estimate just by taking our transformation matrix and raising it to an exponent, can we just do that? Do we have to do the eigenvector and eigenvalue thing? And you know what? I'll leave it up to you. If you want to practice finding eigenvectors and eigenvalues, go for it. If you are just like, I want to just take my transformation matrix and raise it to a big, to a large exponent, that's okay too. I'll leave that up to you. Okay, so you can decide. You're making up your own zombie human apocalypse, and I'll let you decide which way you're going to solve it. Are you going to go for the estimate? This will get you an estimate if you just take your transformation matrix to a high exponent, or are you going to get an exact estimate, an exact answer and find the exact equilibrium values by finding the eigenvectors? That was your choice. And that's it for my helper video. Good luck.